Hi, I'm Yusuf.
Hi, I'm John. Sorry there, we had a few technical difficulties, but I think we have them sorted out and we're ready to roll.
Great. Before we get into the main topic for the week, I hear you have some awesome war stories from the lab this week, John.
Yes, and what I got is, Yusuf, I think you know I do a lot of chip work, right?
Yep. You
And
you uncap the ICs and show the silicon pictures, right?
that's right. Do you know how I open those chips up, typically?
Sometimes you said you ground them down, and sometimes you use chemicals, right?
That's right. So sometimes I'll do both. So I'll grind them down initially a little bit, maybe to make a little cavity or reduce the volume, but then I use nitric acid to open it up the rest of the way. Have you used nitric acid by chance?
I haven't used it, but I do know. Isn't that the bad stuff that only glass contains it, and it eats through like everything?
No, that is hydrofluoric acid, but good news, I have that too. That is not the subject. That is not the subject of this video, but I definitely have stupid hydrofluoric acid stories. No, nitric acid, but it is a wonderful substance. Do you know the book Ignition?
Yes, I have read it, and actually, people should read it. There's a whole bunch of like technical formulas in there, but in between that, it's just awesome story. Like it is extremely well written.
Okay, that's good because you'll have some good context for this. So in Ignition, they talk about a few problems with nitric acid. And one of them that I encounter a lot is that for chip work, the higher the concentration of nitric acid, the better it works. But there's a problem. It can lose concentration for a number of reasons. Do you by chance remember in the book them trying to measure the concentration of nitric acid and what happened?
Didn't things go boom?
Things go boom a lot in that book. Yeah, like mixed acid just destroys everything. But nitric acid, the really big problem is that a lot of acids, you can do this very linear thing. Like I think hydrochloric acid, if you want to know the concentration of hydrochloric acid, you just take some conductivity measurements and like you basically just know how many hydrogens are in the water. That's the concentration, done. But nitric acid, if you may remember from that book, was really complicated. It had all these complex side reactions, and it's very nonlinear. So in the book, they talked about like, yeah, you can kind of do conductivity, but it doesn't work. Do you happen to remember that segment?
Yes, a little bit. It's been a
Okay.
while since I read it.
So yeah, I tried to do that myself because I had to get to understand if my nitric acid was good. And I I basically ran into the same issues. I mostly used a pH meter. I tried like diluting it and all these other things, but it just didn't really work. And eventually what I decided to do was I had heard that one really reliable way to measure it though is density. Have you ever done like density measurements before?
Yeah,
What's the basic principle of a density measurement? Like how would you do that?
I don't remember. It's been a long, long time.
Well, okay, so to get density, it's like, grams per cubic centimeter, let's say, right? So you
Yeah.
basically need two things. You need to know the mass and you need to know the volume, right?
Yep.
Okay, so with that in mind, let's see if I can go over to John's magical lab corner over here, and I'll show you some things to do that. So here, if, can you see, I've got this scale here. Does that show nicely?
Yes.
So this is a milligram scale. In fact, you can see it's tared right here for -1 gram. And the reason why that is that I need something to hold this very caustic acid when I'm taking its weight. And so in order not to destroy this precision instrument, what I've done is, first of all, put a spill tray on here. And then I take these little microfuge vials and I put my acid to measure the weight in there. And I put that on there and I might tare it. And you can see that they're within a few milligrams of each other, which is pretty nice. And this is good because it turns out that even a difference of 10 milligrams or even 1 milligram can actually have a difference of, I'd say 20 milligrams, you'd still get a difference of like 4% on the acid concentration, which is quite a lot, I would say, at a 1 gram level. So you need a very precise setup. So here's the first thing. I was like, great, I have a scale that can measure things very precisely, but that leaves a second problem. If you have the mass, you still need one more thing. And what is that?
The volume.
That's right, you need the volume. And it turns out that measuring volume, especially of a very caustic substance, is a little bit more tricky. So I started out with just some very basic things, like these very crude pipettes. And it became very clear, just due to the extreme precision here, that these were not going to give very good measurements. Have you ever used very precise volume measuring equipment? Do you know what you might use by chance?
Maybe like glass capillary tubes.
Oh, perfect. That's a great answer. Yeah. So you even skipped ahead a little bit. I would say the next thing you might use is a graduated cylinder. But yes, glass capillaries. And I looked and I thought I had some of those, but I couldn't find any in inventory. But I had an idea. Have you ever done biotech work by chance?
No, not really.
Not really. Okay. Have you ever heard of these things called micropipettes? They look like
I've
this.
seen them.
Okay, you've seen them, but you don't know much about them.
No, no.
Okay, so this is called a micropipette, and this is a fixed one. You see it says 100 there. And what
Yep.
that means is that this is fixed for 100 microliters, which is at a very precise level, I believe. And the way that it works is normally going like this, you will press this down until you feel a mechanical stop, and you will extract your liquid then by going like this, move it over to the container you want to transfer it to, and then you'll press firmly down to eject it all the way. And if you look closely, you see that there's a small difference between those two. And so this is supposed to be kind of a precision instrument. And I was pretty sure that nitric acid was not very good for this. Actually, let me demonstrate since we actually have nitric acid over here. I could even give a little backstory. Can you see that this container has, I don't know how well that's in camera view. It's just been destroyed by the acid fumes. Like there's some tape on there and stuff. Here's another great example. This is a fluorinated plastic container. I don't know if the lighting's good enough here. Maybe I can move it over if I have one here.
It's a little blurry, but it's
Yeah,
fairly clear.
I was gonna see if I could move one over. Here we go. This is a good example. So this is my waste nitric acid. So this is fluorinated plastic. The skin on this has been like ravaged by the nitric acid just due to the extreme concentration. And this stuff for practical purposes is considered unreactive, but because the nitric acid can still permeate through here and then it kind of decomposes, it's still destroying this super high quality container. Anyways, so with that in mind, I was like, okay, this is probably really bad for these pipettes. But I said, well, maybe this will work. I've never used this. Somebody gave it to me for free a while back. And so I said, great, I've got all these pipette tips. And I've had these in storage for literally years. I have boxes of these things. First problem, these turn out to not fit my pipettes, which is a little bit depressing. When you've kept around something for years and years because you think that one day, maybe you're going to use it. And then that one day you finally go to try to use it. And guess what? It doesn't work. Like it's not even close to compatible with your equipment. So I don't know. But have you ever heard of the Odin? They sell these biotech kits. Heard of them by chance?
Do they make those like DIY kits you can do like genetic experiments and stuff?
Yes, exactly. So I had a DIY CRISPR kit, and it actually came with the right size tips. So I was able to do this, and then I found out next, this thing is horribly out of calibration. Like it's got like more than a 10% error. I've had this stored in my attic, so I don't know. I guess it got too hot. This is trash, even before I started doing it. But the Odin kit also had one, and I did some tests, and it still worked. So far, so good, right?
Yep. No, before you jump fast, how do you know that was miscalibrated? How do you check that?
That's a great question, because even though that these are not super accurate, these microfuge tubes, I don't know how well it'll show. I think you can see it, just barely.
You barely see some gradations on there.
Yeah, so I'm able to look at those, and I can, within some precision, I would say within 20 microliters, I would say within about 20 microliters, I can determine the accuracy on these. So I could see that it was off by like 100. So it was clearly not measuring right. And then after I switched to the newer one and I saw that it was dead on, I was pretty confident there was something wrong. And something that I didn't do, which I really should have, is although I don't know the density of my nitric acid, I do know the density of water. So what I really should have done to start off with this was I should have measured out 1 milliliter of water, and that would have given me a standard to know how accurate the measurements were. So if I did it again, that's actually a change I would make. But does that make sense?
Yep. Sounds good.
Yeah, so with that in mind, I did this and it's actually seemed to work. And unfortunately, I've cleaned up the damage already a little bit, so it doesn't look quite as bad, although it's not good. I knew this wasn't good for the micropipette, but I thought that I could get away with doing this at least for a little bit. Unfortunately, after only taking something like 10 samples, because I have to take, or maybe 20, because I have to take, it's only 100 microliters. I wanted 100, I wanted 1 milliliter per sample I was running. So I had to do a few samples and all this. I think by the time that I put this in there like 30 times, the bottom had melted. I don't I've cleaned it up with sandpaper a little bit now, so it doesn't quite look as bad as it did. But this was like dripping plastic. And mind you, this never went into the nitric acid. It's just that the fumes from this, the pure nitrogen dioxide, it's like pure red liquid death, or gassy death, which I don't know. You can see that like that red color, right? Like don't breathe that, I mean, I could waft it for the camera. I don't know. But anyways, yeah, that red gas just destroyed the pipette, not even touching the acid. So I don't know if that pipette works anymore, but I was never really going to use it. I've had it for years, I think. And I did get to measure the acid. So I think that's mission success. And for our readers, the last thing I'll say is the original backstory was I got this bottle of nitric acid yesterday at a Whole Foods parking lot, because of course that's where you get all of your high concentration nitric acid. And I wanted to know what concentration it was. And so the original point of the experiment, which I've transferred now to this bottle, was to figure out what is the concentration of this acid, because I require at least 90% acid for it to be useful for my chips, more or less. And I assayed this, and it's only about 82%. So it looks like it actually may not be concentrated enough. And you can't really tell just by looking at it, but this is stuff I have from Sigma Aldrich. And I assayed this, and I would say it's at least 94%, maybe 96%. So this is much better. This is good. And unfortunately, this, I don't know if I'll reprocess it or what. Maybe use it for some less important chips. But yeah, unfortunately not usable, at least as I use these chips today. So anyways, that's mostly what I had there. I hope you found that fun and entertaining.
Yeah, no, that's some real practical engineering right there.
Oh, and last thing I should say, I have ordered a glass volumetric pipette, which I believe is more or less the most accurate measurement piece of glass where I can get to do this more properly. So hopefully within the week, I'll get that in the mail, and then I'll repeat this, and maybe it won't even destroy the pipette in the process. So we'll see.
Okay, that is a pretty cool story, John.
Cool. On to the main topic.
Yeah, main feature. Let's go. So this last week, I've been digging into the rabbit hole of metal finishing. We did a little CNC project last week. We were waiting on the actual parts to come in, and then I thought, how do you protect these parts from corrosion? How do you do it? And there's a whole world of this, right? So there's like tons and tons of different ways of doing this. I actually wanted to pick out a couple that are, I think, super accessible to like pretty much anyone. You don't need really any special equipment. You don't need, any special processes, and they're kind of interesting. And one of them is hot gluing, which we'll get into. Which I think you ran an experiment this week, which was super successful. I mean, when you sent me the picture of your samples, I thought that was a stock photo. Like the clarity and consistency of those samples were like pretty spectacular. And I want to dig into that.
Okay.
That success in a bit. And I tried something as well. I tried engine turning, which turned out to be a horrible failure. But there's a reason for that.
Do you want to talk about engine turning? I don't know.
Yeah, so what do you want to do? Do you want to do the success first or the failure first?
We want to leave on a positive note, I guess. So maybe we talk about the failures first.
Okay, so let me present this. I want to show you a picture of what engine turning should look like. Okay. This I think is mostly a decorative kind of finish on metal. It doesn't really protect the metal, although like some gunsmiths who still use this kind of to decorate the guns do say that it captures the oil a little better, which kind of makes sense because you're roughing up the surface. Okay. So it gives you some protection, but it's, I think, primarily a decorative process. So let me go ahead and present this for you. Let's go. Okay.
Oh yeah. Okay.
Yeah. Hopefully you can see this. So it's a very simple process, right? So you take something round, and you kind of like using a drill, press against the metal in consistent in a consistent pattern, and you get this like nice, like jeweling type pattern. So this is called engine turning or jeweling, and it's used, it's used in watch parts, like high-end watch parts. You'll see, if you can look into uh, the parts, you'll see this pattern. It's used in cars, actually older cars, like vintage cars had these on the dashboards.
Did they have them on the engine?
No, they did not have them on the engine.
Okay.
But you could do that. Like you literally could do this. Like I think on pretty much any metal surface, right? The Spirit of St. Louis, the plane.
Oh yeah.
That actually had it on the engine cowl on the outside.
Oh.
Yeah. So this was. I mean, I think this is an older kind of style finish. I don't think you see this as often. But I've seen some samples. People have done it on their tools, like their pliers and things like that. And it's a very pretty pattern if you get it done. So okay, here's my foray into it, right? So I don't have specialized equipment. I thought I could do this at home. I took these things, which are a drill,
okay,
some toothpaste, and the eraser tip of a pencil.
Okay.
Okay, and then you see the little metal sample that I drew some lines on. I was going to do it on that, right?
Yeah. Okay. Yeah.
Okay, so that didn't work.
What happened?
So it barely made any scratches or any marks on that particular metal little part.
What, I'm sorry, we're using a brush there. I can't quite see what's on the end of the drill there.
Oh no, so that the pencil hasn't been added onto that yet.
Okay.
Basically what I did was I cut the pencil off and I stuck the eraser tip sticking out onto the drill.
Ah, yes. Okay.
And the drill was going to turn the little eraser and using toothpaste make the marks on that little milk thing, right?
Sure.
Didn't make anything on that. So then I thought maybe, what's a softer metal? So I went for some aluminum foil.
Okay.
If I can get to the tab. Here we go. You see this?
Yeah.
So this is, So this is basically aluminum foil and me using the drill, the eraser tip and some toothpaste to kind of try that pattern. And you see that there's something there, right? Like it looked better in person, but not a great finish, right? And as any good workman, I'm going to blame my tools. Okay, so the drill I think was the key. It's a 20-year-old drill. We could do a whole episode on my relationship with this particular drill, but I think the two problems here were, one, it's hard to hand hold this, especially if you want to do a consistent repeating pattern. It kind of like swirls itself around. So I think hand holding it was a problem. And also the drill's kind of crappy, like it has no power, right? So it didn't really do anything. And I've seen many videos.
But is this a high power operation? It seems like kind of a delicate operation to me.
You can be, I think, a little rough. I mean, it does need to make those marks, so it needs to kind of like grind in a little bit. I mean, it's super tiny, like it's very minimal. You can barely feel it, but you do need to, for a few seconds, run that in, put a little pressure, and it needs to be consistent, right? Like while I'm hand holding this thing, it was kind of swaying all over the place. I couldn't get that like consistent pattern. If you move at all, it's gonna destroy the pattern.
Gotcha.
And I know for sure, like many people have tried it out with, the eraser tip and toothpaste and have gotten like pretty good results. I think the key here was you need a drill press because, it keeps the tip like very consistent and straight on, like perpendicular to the metal, and also lets you control it. So I think that was the key. I mean, if you might be able to do this handheld, but you definitely need, I think, a little more powerful drill than the one I have, which is like really, really useless.
Gotcha. Now, one thing I'm surprised is you didn't tear the aluminum foil. Was that not a concern? Because that's quite fragile, right?
It was, but like, as you can see, it did make some deeper marks on there, but generally, no, it was fine. It actually held. I did put on like a silicone mat, like a rubbery mat, which kind of held it in place. So
okay, that might help.
Yeah, it wasn't flying all over the place. But in person, you can kind of see the starts of, the effect that I was wanting, right? Which is the original, like the jeweling pattern.
Another thing I have to ask too is it looks like I see concentric score marks. Did you have something that was sticking up that was making those?
You mean those like the hard lines?
Yeah.
I think that was because the angle while I was holding the tip was angling in, and kind of the edge of it was pushing in.
Gotcha.
Yeah,
Very nice.
overall, I think this is pretty accessible solution. If someone's got a drill press, I think there should be no problem. Like just take some toothpaste, take a pencil eraser, and you'll be good to go. Ideally, there's this thing called Cratex which you'd use, which is like this rubber rod which has kind of the little sandpapery bits in it, and you'd use that. But you could do this at home like pretty easily.
Oh, very nice.
Yeah. Oh, well, on that fail, let's get on to your success, because I really want to figure out how you did this, because your samples are super consistent. Do you have a picture?
I was going to say, if you had the picture handy, that actually might be easier.
I do actually.
Yeah, why don't you bring that up? Because I've tried to put these on the camera, and it's a little bit difficult. So, although it's probably going to show me though while I'm talking, so this may not actually work.
Yeah, I think it shows both of us. So, so what you're seeing on the screen are the samples you sent me, and I mean, I initially I thought this was a stock photo, just because of like the difference in color and the consistency of color, right? Do you know a background of this process, or do you want to give a little background about it?
Yeah. So let me see if I can bring up this image real quick, so I can. Let me see if I could share my screen maybe with this image up. Just one moment. And I'm going to share. Or not.
Okay, how about I can give a little background while you find that image?
The issue is it only wants me to share your screen. It looks like it may be difficult.
I can stop sharing then.
Yeah, why don't you try stop sharing?
Okay, there you go.
And then maybe I can hit share now. Great. Okay, great. Can you see my screen now?
Yes, I can see your screen.
Okay. Yeah, so let's talk about what happened here. So the basic idea, and honestly, I'm less familiar with the technical. I have a guess. The background was we were talking about this, and the idea was you can heat a piece of metal, and if you heat it just right, you get what I presume are thin film interference. Is that correct?
Yes. So basically, this particular hot bluing or bluing, steel bluing works on like iron-based substances, right? Because it's basically the iron oxide that you're creating, the iron oxide layer. You can create different oxide layers for different metals, but they don't happen the same way. Like titanium does it electromechanically. Aluminum anodization is also a mechanical, chemical mechanical process, and aluminum doesn't actually show these colors. So this is very much relegated to like iron-based substances.
Okay, so I'm going to stop sharing and I'll show the process a little bit, and then we'll go back to this image because it's a little bit hard to see these colors on camera. They really look beautiful in real life. My camera just doesn't show them very well. So I'm going to hit stop so you can see my video feed again. And so the question was, how do you very precisely heat the metal then to grow these layers in just the right way? And the first thing I tried was just to use a torch, because fire is awesome. Unfortunately, and we'll see if this shows on camera, when I was doing this, can you see that there's one corner that's kind of discolored a little bit?
Yes, and that's what I was expecting. Like when I was expecting to see your results, that's what I was expecting.
So yeah, and then the other thing you should notice too is if you look very closely, there's kind of this rainbowy pattern, and then it goes to kind of a dull blue. Now, earlier in that image I had, we started with basically the raw steel on the left and this dull blue on the right, or dull gray. I don't know what color you'd call that. It's kind of a bluish gray. And so what that basically means is it's my right of this has been heated strongly to go through all of these colors. And then the lower left, on the other hand, hasn't been heated at all. So it's still cold essentially. And that was because I took some pliers. If I get some pliers for reference, and I had basically held it here and waved this. I tried to be really careful with the flame, but got it kind of close there. And I did a few experiments and try as I could. It was just really difficult to get any sort of really even temperature on here. I tried moving it really far away and moving it in. I tried alternating where I held it, which helped a little bit. I think somewhere around here, I have one where I did do it with that and I got it pretty close to looking reasonable. But ultimately, I decided this really wasn't the right way to do this. But if you do remember, I have a tool that I'm very fond of that generates a lot of heat. Do you know what that tool is?
What is that tool, John?
It is my trusty temperature-controlled heat gun. So
how hot does that get?
Well, so yeah, there's a little bit of a fine point there. Its set point goes to 1100 Fahrenheit. Do you know roughly what is the temperature that this process requires?
So at different temperatures, you get different colors. So it starts, I think, between like 200 to 300, you get the light browns.
Is that is that centigrade or Fahrenheit?
No, Fahrenheit.
Really? Okay.
Yeah. And then you at about 590 is where you get the purples.
Okay.
Like darker, lighter purples and the blues, and then it goes to the black oxide, which is the thicker layer.
Sure. I didn't get black oxide, but we can talk about that. So what I did then, what I found worked really well, is I made two changes. First of all, I went to the heat gun, and if you can see this on the table, I can just set it down like this. So it just rests on the table. I can set a set point on the side here. And then what I did was I switched from the pliers, which are very large, to, and I also had to hold it, to these, what do they call these things? Stats? What do they call them? Use them in medical. Anyways, you know, hemostats.
Is it a forceps? That's not a forceps, right?
Forceps? I don't know. Maybe forceps. The tool. Anyways, it clamps it. It's smaller. So that's one of the big things. It's smaller and it clamps it easier. So then what I did was I took the metal and I grabbed it by just the itty bitty corner. So it's just barely on here. And I waved it back and forth. Originally, I didn't wave it, but I found that the heat gun wasn't quite even enough to get an even just by itself. And then what I did was I played with the temperature profile at the bottom, and eventually I settled on that setting it to about 1010 Fahrenheit gave really good results over about a minute or 30 seconds to a minute. So it would very slowly heat up. And by waving it back and forth, I would visually look to see what it looked like. And then at some point, when it looked good, I would just pull it out. And I think initially I rotated a little bit where I held it a few times just to get that nice consistency. But once it was held just barely in the corner and I was waving it out, it didn't seem to even discolor where I was holding it and gave really excellent results. And so, yeah, by doing that, I was able to get all these different colors that you saw there.
Did you do an oil quench at the end?
I did not. So traditionally, when you've talked about the black oxide, that's what I've associated with that. In fact, I've done it in the past though, so I don't know how black this looks, but this screwdriver had gotten super rusty. So one day I cleaned it up with some sandpaper, torched it, and then I dumped it in basically kerosene, I think it was. And it did put a fairly large black oxide coating over it.
Okay, so the color I don't think is caused by the oil. The oil, I believe, is mainly used as a water displacer to prevent corrosion, because the oxide layer doesn't prevent corrosion that much.
Okay.
So if you heat it higher, like maybe 600-700 degrees, I think you will just get the black color, which is really? in your last piece you kind of got there. You had the grayish color.
Yeah.
So I think the oil quench is mainly as a water displacement for corrosion purposes.
I see. Okay, gotcha.
But no, those were like super consistent. Like that, they're impressive. I was expecting the blotchy kind of colored samples, because if you're trying to hand hold it over a stove or over propane burner, I think that's what I was expecting you'd get.
Yeah. So I would say, yeah, if you have a small part, heat gun seems to work really well.
Right.
So I would encourage you to try that.
What I was thinking was maybe an oven, a temperature controlled oven, might get you like consistent temperature around the whole part, and you're not, like moving the part around to get even heating. Maybe I'll try that. I mean, I think even my home oven gets to like 450 or something. So right, at least the lighter brown shades might be something you can pull off.
Sure. I think you had also asked one more thing you wanted to see. Is that right?
What was that?
You had asked about the sputter coater.
Yes. You know, I've been to your place, and although the sputter coater isn't actually, you know, metal finishing device, it does deposit metal onto things, right? So kind of related, but I thought it was a pretty interesting piece of equipment.
Yeah,
Do
so
you
I was
do you
thinking,
want to go ahead and sorry? Oh, no, go ahead.
yeah, I was gonna say maybe we just talk about it real briefly because I think there could be a
Mhm.
full episode. But just to touch it on briefly since you asked. So yeah, sputter coater basically mechanically uses a plasma to basically shoot, say, gold in this case, atoms at something, and you can coat things. This was some aluminum that I put some gold on, and this was some silver. But one of the things we found out, for example, with silver, which isn't as visible on this, but really visible on some other things, if you don't match the metals well, because it's gold on silver, they don't really alloy well together. It's actually very weak and kind of crumbles apart. So in order to, if you want to start doing some more advanced experiments with a sputter coater with me, I think we would have to put a lot more effort into pre-coating the materials if we want the coatings to actually be durable.
And would those be just you know, like the electroplating stuff that we did as well, like copper electroplating the silver?
Yeah, I think we'd use electroplating to basically prepare a surface coating, and then we would finish it with a sputter coater, say with gold or something like that.
Okay. Yeah, I think the sputter coater could, you know, have its own episode. Like it's a pretty interesting piece of equipment, and the application is interesting, right? Because you use the coated samples for what, your electron microscope?
Yeah, very thin conductive layers on the samples. So just for reference, since I happen to be in my garage, uh, this is my little small electron microscope with a Hitachi brand Hula Girl on top. And yeah, so in order to put in here, if you don't put a coating on them, when you shoot electrons at the samples, they can build up charge and they'll start repelling the beam and you don't get good images. So yeah, you'll get much better images if you put a very thin coating, say out of gold, on top of them.
But could you get like at least an initial image, or like is it not possible if it's not
Yes, you can.
if it doesn't
In
have the
effect, yeah, I mean, this would be part of a much longer conversation, and somebody like Adam McCombs, I would say, would be a much better expert on this. But my SEM is a very entry level SEM. The main advantage of that SEM was like including shipping and everything. I think I paid like $2,200 for it, like included all the pumps and everything. And as far as electron microscopes go, like for something with modern digital capture, like that's a pretty low bar. The disadvantage though is that SEM has a resolution of only maybe 30 nanometers. And if you start looking at like a nice SEM today, you're talking about sub nanometer. So the resolution of that is so relatively poor that a lot of the advanced techniques about like, you know, how well you coat something and all that, at least on this particular SEM, don't matter so much. But if you got one of these higher resolution SEMs, it turns out, for example, that the grain properties of gold will start affecting your image quality. And then you might have to use something like, geez, I think like platinum or something has better imaging properties. But since my SEM is so basic, yeah, I can even maybe not coat something and it won't affect the performance that much in many cases.
Okay.
Yeah.
Okay. Well, on that note, I think it's a good time to stop.
Sure. Sounds good.
So, you know,
Do we have any questions? I was trying to bring
no,
that up.
we don't have any questions right now. So,
Okay.
but people should tune in and send in your questions. You know, we'll answer them as they come up. If you've watched all the way till here, please don't forget to subscribe, like, and comment. Thanks a lot.
All right. Until next time. Bye.
Bye.